Okay. So we continue with local extrema. Now, in a previous lesson, which is recorded on the Microsoft Teams site, I explained the algorithm, but I shall remember a little bit. So first of all, if we have a function of several variables and we want to compute its local extrema, the main steps are: first, compute the partial derivatives, then solve the system which gives us the critical points. The solutions of this system are called critical points. Then compute the second order partial derivatives. Yes. Then fourth, for each critical point, for each A, which is a solution of this system, we compute the Hessian matrix, which contains the second order partial derivatives at the point A. And now everything is decided by the sign of the eigenvalues of the Hessian matrix. So the sign of the eigenvalues of the Hessian matrix. More precisely, if all the eigenvalues are strictly positive, A, it's a minimum. If all the eigenvalues are strictly negative, then A, it's a maximum. If there are both positive and negative eigenvalues, A, it's not an extremum. In other cases, we decide directly by studying the sign of the subtraction f of x minus f of a around a. What sign is it? We shall see. Okay, so this is very shortly the algorithm. And now let's proceed to some examples. Okay. For example, let's take f of x and y to be xy times logarithm of x squared plus y squared. Here the domain of definition is the entire plane without the origin. So the pair xy must be different from 0, 0, obviously. So we shall follow the previous algorithm. So we can first compute the partial derivatives. We have a product here. Plus xy times 2x over x squared plus y squared. So here we have y logarithm of x squared plus y squared plus 2x squared y over x squared plus y squared. There will be a problem here if we can solve if we can find the critical points. We shall see if this can be done. Okay. Similarly, by symmetry, we can write directly, because the function is somehow symmetric between x and y. And here we shall get plus 2x y squared, and below have x squared plus y squared. Now let's see if we can compute the critical points. So if we, of course, the system can be written y times logarithm of x squared plus y squared plus 2x squared over x squared plus y squared equals 0. And x times logarithm of x squared plus y squared plus 2y squared over x squared plus y squared equals 0. Now, obviously, we have x equals 0, y equals 0, but these are not in the domain of definition, of course. And the problem is that if we have other solutions, for example, if x equals 0 and y is not 0, yes, then and y is not 0, then necessarily this parenthesis must be 0. And if we put here x equals 0, we have logarithm of y squared equals 0, which gives us y equals plus and minus 1. So we have 0, 1, 0, minus 1. Yes. And now the other case is when y is 0 and x is not 0. So if y is 0, this equation is fulfilled. And if x is not 0, then but y is 0, then we have logarithm of x squared equals 0, and it gives us x equals plus minus 1, and we have the solutions 1, 0, and minus 1, 0. Okay, these are the critical points. It can be proved that these are the only. So now, we must decide the nature of these points. So for that, we need to compute the second order partial derivatives. It's a little bit of work here. These are the first order partial derivatives. So now let's compute the second order partial derivatives. So first of all, they're not mixed. We need to compute the derivative of der on def to der on x with respect to x. This here we have der on def to der on x. So we have 2xy over x squared plus y squared, because y is a constant, and here the derivative is 2x over x squared plus y squared plus, and now this one we must differentiate it with respect to x. So it gives us x squared plus y squared squared, and above we have, okay, 2, it's a constant, we put it in front, and then here we need to differentiate with respect to x. Yes, it will give us 2xy times x squared plus y squared minus x squared y times 2x. So we obtain 2xy over x squared plus y squared plus 2 times, here we have 2x at 3y will vanish with this one, and we get 4 x, sorry, 2, no, 4. 4xy at 3 over x squared plus y squared squared. This is the derivative 2 times with respect to x. Now, by symmetry, we can compute the other not mixed partial derivative of second order by changing the place of x and y. So it is 2xy over x squared plus y squared plus 4x at 3 y over x squared plus y squared. Let's hope it's okay. And now we still need to compute one second order partial derivative, which is the mixed one. Der on to f over der on x, der on y. We can differentiate here with respect to x. So it is logarithm of x squared. Yes, please, if you have some observation, please tell me.
No, I wanted to respond. That is with respect to x.
Yes, this one with respect to x, yes. So it will be, it's a product. Logarithm plus 2x squared over x squared plus y squared. Yes. And now plus the other term, this one, differentiated with respect to x. Okay, 2, it's a constant. I shall put it in front. And now we have with respect to x, yes, it's y squared times x squared plus y squared. Negative x y squared times 2x over x squared plus y squared squared. So you need to differentiate with respect to x, yes, y. Okay. So this gives us logarithm of x squared plus y squared plus 2x squared over x squared plus y squared. And here we get what? Plus 2 times. Okay. It will be x squared y squared. Then plus y at 4. And then minus 2 x squared y squared over x squared plus y squared squared. So finally this will give us y at 4, which is a little bit strange because it must be somehow symmetric in x and y. Something it's so I need to differentiate this one with respect to x, yes?
Yes.
So until here it was okay. X, y times 2y. Okay, so again, logarithm of x squared plus y squared plus, it will be x times, below we have x squared plus y squared, and above we have 2x. So it's okay, 2x squared over x squared plus y squared, and here plus, now this term, 2, we put it in front, and we have xy squared differentiate with respect to x, it's y squared times x squared plus y squared. Yeah. Negative. Now, xy squared as it is times the derivative of
the denominator. Yes.
With 2x, yes? It's okay, it's okay. If we, it's symmetric, it's okay, but we observe the symmetry only if we take here the common numerator, denominator. You understand? Because I was a little bit preoccupied because this I don't see the symmetry between x and y, but it is if we consider this one. So it's okay, but we shall not consider the common denominator. So finally, this is simply 2 times here it will be y at 4 minus x squared y squared. So it's okay. Y at 4 minus x4, x at 2, y at 2. Okay. If you would, but we don't need to do it, consider here the same denominator, then this expression would be symmetric with respect to x and y. Yes, because the initial function has a symmetry between x and y. So there on def to there on x, there on y must be somehow symmetric in x and y. And it is. But we can't see it in this form. If we consider here the same denominator, it will be symmetric. Okay. So now, let's write the Hessian matrix at each critical point. So the Hessian matrix at the point 0, 1. It will be. So the second order partial derivatives are written here. We put x equals 0 and y equals 1. This is 0. Yes, this one.
Yeah, and one is so.
This
0.
one is 0. Here we have logarithm of 1 is 0. Here it's 0. And here we have what? We have 2 over 1. So here
Yes.
it's 2. 2. The characteristic polynomial will be minus lambda 2, 2 minus lambda, which is lambda squared minus 4. The eigenvalues here are plus and minus 2. So 0, 1, it's not an extremum. Yes?
Yes.
Okay. And so on for the other. The only question here at this exercise, if there are, so for the other critical points in a similar way, it's not a problem. The only question here is if there are other critical points. I mean, if this system has other solutions too. What I can see from here, if for instance, these two parentheses vanish, so if x is different from 0 and y is different from 0, then these two parentheses must be 0. So the subtraction must be 0, which means that finally the logarithm vanish and we get that x squared minus y squared must be 0, which means x equals plus and minus y. So one must check if there are critical points with x different, with both x and y different from 0, but in that case, y must be plus and minus x. Let's consider this case. For instance, if y equals x, what happens here? We get logarithm of 2x squared here. Yes, we replace it. Plus 2x squared over
2x squared.
X squared, it's 1. It's 1, yes? Equals 0. That means logarithm of 2x squared equals minus 1. So 2x squared equals 1 over e. So we can obtain x equals plus and minus root of 1 over 2e. And now we must check that this vanish here, this expression, which is not the case. If you now replace x and y both equals to 1 over root of 4 to e, here you don't get 0. Yes, so these are the only critical points. This is the idea. But okay, so here the difficulty was about solving the system which gives us the critical points. All the rest is somehow straight, and also the computation of the second order partial derivatives sometimes is a little bit tricky. Let's take this one now. F of x and y equals x at 3 plus 3xy squared minus 15x minus 12y. Of course, here the domain of definition is r squared. So the first order partial derivatives are 3x squared plus 3y squared minus 15. There on def to there on y equals 6xy, yes, minus 12. Okay. And now the critical points. From here we get that x squared plus y squared equals 5. And from here xy equals 2. From the second equation we take that y equals 2 over x. Yes. And we replace it in the first equation. So x squared plus 4 over x squared equals 5. Yes. So we get that x at 4 minus 5x x at 2 equal plus 4 equals 0. This is a if we put here x squared equals t, we get a quadratic equation, t squared minus 5t plus 4 equals 0, which gives us t equals 1, t equals 4. So x squared equals 1. We get x1, 2 equals plus and minus 1. X squared equals 4. It gives us x3, 4 equals plus and minus 2. And now we compute the values for y. Y was 2 over x, remember? So here y equals plus and minus 2. And here y equals plus and minus 1. So we have 1, 2, minus 1, minus 2, 2, 1, minus 2, minus 1. These are the critical points. Yes. And now we need to compute the second order partial. What's interesting, this is what I was looking a little bit careful here. What's interesting to this function is the following. The function has no symmetry between x and y. However, interestingly, the partial derivatives are symmetric in x and y. Yes, there is a symmetry of the partial derivatives for both, but the function is not symmetric in x and y. Okay. Now, the second order partial derivatives, this is 6x. The not mixed first, this is 6y. Yes, again, the symmetry is continued. And
it's not 6y.
Sorry, it's
6x.
6x. Of course. And the mixed is, this is 6y. 6.
Yes, 6y.
So the Hessian matrix at some arbitrary point will be 6x, 6y, 6y, 6x. Yes. It's always a symmetric matrix, of course. And now the Hessian matrix at the critical points. So the Hessian matrix at 1, 2. It is
6, 12,
6,
6,
12, 12, 6. The eigenvalues are given by the equation
6 minus lambda squared minus 12 squared
minus 12 squared. Which this is the characteristic polynomial, which means 6 minus lambda minus 12 times 6 minus lambda plus 12, which means minus lambda minus 6 times minus lambda plus 18. The eigenvalues are lambda 1, it's minus 6, lambda 2, it's 18. So the point of coordinates 1, 2, it's not an extremum because we have both positive and negative. Okay, the next one, minus 1, minus 2. The Hessian matrix at minus 1, minus 2 is minus 6, minus 12, minus 12, minus 6. The eigenvalue, the characteristic polynomial will be minus 6 minus lambda, minus 12, minus 12, minus 6 minus lambda, which means 6 plus lambda squared minus 12 squared. So again, we shall have a mixed sign. obviously, yes?
Yes.
So again, it's not an extremum, and so on for the other two. For I, let's see the third one. Okay, see, matrix at 2, 1. It is 12, 6, 6, 12. The characteristic polynomial will be 12 minus lambda 6, 6, 12 minus lambda, which means 12 minus lambda squared minus 6 squared. So it is 12 minus lambda minus 6 times 12 minus lambda plus 6. So it is 6 minus lambda times 18 minus lambda. So both are positive.
And
So the
yes,
point of coordinates to 1, it's a minimum. Yeah. Similarly, I think minus 2 minus 1 will be a maximum. So from the 4 critical points, 2 of them are not extrema, the other 2 are extrema. Okay. Let's try something in 3 variables. Okay. In 3 variables. Let's see. Let's try this one. Let's see if the computations are straight. We shall check. You have many other solved exercises in what I put on the Microsoft Teams platform, and I try to not to solve those exercises. You understand? In the books I put, in the materials I put on Microsoft Teams, you have other solved exercises. Yes.
Okay, thank you.
Okay, let's try this one in 3 variables. F of x, y, and z equals x plus y squared over 4x plus z squared over y plus 2 over z. Yes. Here, x, y, and z must be different from 0. So let's check again. X plus y squared over 4x plus z squared over y plus 2 over z. Okay. Okay, let's start to compute the partial derivatives of first order. 1 minus y squared over 4 squared. Yes, this is the derivative with respect to x. Here we have z, yes. Let's write it in a proper way. Okay. Now there on left to there on the y. That will be 2y over 4x. That means y over 2x minus z squared over y squared. And now with respect to z, that will be 2z over y minus 2 over z squared. So please tell me if you got the same values. We must be a little bit careful here in 3 variables. There is work. Okay, now we need to find the critical points. So we obtain the same partial derivatives, yes?
Yes.
Okay, and now let's try to solve the system. From the first equation, we have that y squared equals 4x squared. It can be written like this, yes?
Yes.
From the second equation, we get that y at 3 must equal 2x z squared. And from the last equation, we get that z at 3 equals y. Please check if you got the same results.
Yes.
Okay, and now we need to solve this system. Okay, we shall use substitutions. We need y. Okay, so y it's z at 3. This is it seems to be the simplest way. We replace y but z at 3 in both these equations. So y squared means z at 6 equals 4x squared. And the second one is, sorry.
Z.
No, sorry. We replace y by, yes, it's okay. And here it is z at 9, yes, equals 2x z squared. Now, from the second equation, we get z equals 0. And from the first one, we get x1 equals 0 and y equals 0. So a first solution is when all the variables are 0. So we have 0, 0, 0. Now what happens if z is not 0? From here, if z is not 0, we can simplify by z, yes. So we get that
Z at 7 is
7 equals 2x. So x is z at 7 over 2. And we replace it in the first equation. So we get that z at 6, and don't forget z is not 0. Z at 6 equals 4 times x squared means z at 14
over 4.
Over 4, yes. We simplify, and we get that z at 8 equals 1, yes, which means z equals plus and minus 1. Okay, so if z is not 0, then it must be z2 1 and z3 minus 1. Consequently, if z is 1, x equals from here 1 over 2 x2. And if z is minus 1, x3, it's minus 1 over 2. Because here we have z at 7. And finally, y. So z equals 1, x equals 1 over 2, y is z at 3. So it is 1, and here y3, it's minus 1. So I think we've obtained the following critical points: 0, 0, 0, which is not good, of course, because remember the domain of definition. And we have 1 over 2, 1, 1, and minus 1 over 2, minus 1, minus 1. These are, we have two critical points. Yes. Tell me if you got the same.
Yes.
And now we need to work a little bit harder to compute the second order partial derivatives. Okay, there on def, there on 2f over there on the x squared. Here, this is 0. Here we differentiate with respect to x. It will be minus y squared over 4 times 2 over x at 3, yes?
Yes.
With plus, sorry. It was a minus and we have a second. So that means y squared over 2x at 3. Okay. Now, with respect to y, 2 times, it will be 1 over 2x plus 2z squared over y at 3. And the last one, with respect to z, it's 2 over y plus 4 over z f3. These are the not mixed, but please compute them and to check if we got the same.
Immediately.
Okay, of course, we have enough time.
Yes, I got the same.
Now the mixed. Let's compute the mixed. I got these values, but please check carefully.
Nu înțeleg ceva.
Spune. Ok.
La d squared f by dx dy, am derivat...
Asta?
Da, am derivat în funcție de y. Nu, m-am uitat eu. M-am uitat prost, m-am uitat la derivata a doua, de ordinul 2. Nu, e ok.
So here this one can be computed into two ways, yes, because of the Schwarz symmetry theorem. By differentiating this one with respect to y, and or by differentiating this one with respect to x.
Yes.
Both ways give us the same result, of course, which is this one. Okay, so now let's see the Hessian matrix at the first critical point, 1 over 2, 1, 1. Okay, so we put x equals 1 over 2, and so on. This is what we have on the main diagonal, and this is what we have on the other points. Okay, so here we get what? 1 over 2 times 1 over 8. That means 4. Yes?
Yes.
Now, here, minus 1 over 2 times 1 over 4, which means minus 2. Here, this is 0. Here is minus 2. Here it's minus 1. Sorry, 1. 1. So x equals 1 over 2. So it's 1. And here we get plus 2. So here it seems to be 3. Here we have minus 2 over 1. So here is minus 2. Here is 0. Here is minus 2. And the last one, which is this one, it's 2 plus 4. Seems to be 6. Please check carefully if you have the same matrix.
Yes.
Okay, very well. And now let's see the polynomial, characteristic polynomial, yes?
Yes.
We need to compute this determinant of order 3, but it's not complicated because we have 2 zeros, so it must go So let's compute carefully.
Minus 46 lambda.
Da. Plus 46 lambda and plus 32. Okay?
Yes.
Now, what we know from the theory that the eigenvalues for a symmetric matrix, and this is a symmetric matrix, are always real. So here, because they are real, we can look to the relations between. Now, of course, we need to somehow to solve this equation or to find the sign of the solutions. Or as we can see here, the sum of the three solutions is 13, which is positive. Yes. Then the second sum from the relations with the coefficients is 46, again positive, and the product is again positive. Yes, it is 32. So all the roots of this polynomial are positive. So that means our point is a minimum. So the point of coordinates 1/2, 1, 1, it's a local minimum. Similarly with the other one. Yes.
Yes.
Okay. This is the kind of exercise that will be at the exam. So the functions will be polynomials, or maybe rational functions like here. Yes. So more or less other solved exercise. I told you there are. I put on the, so you can find them on the Microsoft Teams. I didn't put them on the Moodle platform yet. Let's see if we can find another one. For example, let's see this one. It will be shorter with 3 variables again. For example, f of x, y, and z equals x, y, z, negative x, negative y, negative z. Of course, the domain of definition is the entire space. And let's see how we can do it. So first of all, we compute the partial derivatives. Okay, these are the first order partial derivatives. Now we need to solve this system. Okay. Now let's see how we can do it. We can do it in several ways. For example, from now we first observe that from these three equations, it results that none of x, y, and z can be 0. X cannot be 0, y cannot be 0, and z cannot be 0, because if one of them is 0, then the left side of
the relation is not
must be 0. So x, y, and z cannot be 0. And now, because of that, from the first two equations, if we subtract them, yes, we get that z times y minus x equals 0. But z cannot be 0. So necessarily, x must be equal to y. Yeah?
yes.
And because of that, from the last equation, we get x squared equals 1. So x can be 1
Or minus 1.
or minus 1. Yes. So similar now and y must be equal to x. And similarly, and from here we can say, so the only solutions are 1, 1, 1, and minus 1, minus 1, minus 1. Okay. And now the computations are simpler this time. The second order partial derivatives are on the main diagonal, we shall have 0.
Oh, yes.
And now what we have on the other positions?
dx dy.
For example, this one will be z. Yes. This is y, and there on y to there on z will be x.
So x.
So the Hessian matrix at some arbitrary point can be written 0, z, y, z, 0, x, y, x, 0. Yes, this is the Hessian matrix at some arbitrary point. And now at 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Here the characteristic polynomial is minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda, which can be computed by adding all the rows to the first one, for example. So we add the second row and the third row to the first. So we get 2 minus lambda, 2 minus lambda, 2 minus lambda, 1 minus lambda, 1, 1, 1 minus lambda. From the first row, we have a common factor minus lambda. So 1, 1, 1, 1 minus lambda, 1, 1, 1 minus lambda. Now we can, this one can be computed with a triangle rule, but not necessarily. We can simplify it a little bit. For example, if we take the first column and we subtract it from the other two columns, yes?
Yes.
We get here 0, 0, 0, 0, and minus lambda minus 1. We developed it from the first row. So we get 2 minus lambda times lambda plus 1 squared. So we have lambda 1 equals 2, and the lambda 2 and lambda 3 are equals with minus 1. So our point is not an extremum.
Yes.
Yes, and so on. Okay. This is the algorithm. If you have some questions, so the computations will be at this level, not more complicated, because we are not interested in complicated computations. We need to know, we need to check if people can apply the algorithm. That's all. And
So,
from linear algebra, we must know how to compute some eigenvalues. Yes, please.
yes, I have only one question.
Yes.
I didn't quite understood how we have to compose the Hessian matrix for the three variables partial derivatives. I mean, I know that on the principal diagonal we have the second order partial derivatives, but I don't know in which order I have to put the mixed ones.
It's very simple. The definition is this one: theron to f over theron xy, xi, xj. This is the Hessian matrix at some point arbitrary point A. Yes, this is the definition. Now let's apply it. So it's the order of the variables. If, for instance, two variables, x and y. Yes.
Yes.
So x1 is x, x2 is y. So the Hessian matrix will be here. There is only one choice. Actually, you cannot do it in. You cannot take it wrong. Yes.
Yeah.
Okay. And now in three variables, the Hessian matrix will be like this. On the main diagonal, of course, we have the not mixed. Attention, here we have theron to x, according to the theory here. Theron x1, theron x2, because we are on the first row and second column. Yes?
Oh, okay, I got it.
So in xy, we have
dx and dy.
Exactly, x,
And
y. Here we have theron to f
and
over theron x1. We are on the first row. And on the third column, it will be right. So that means theron x and theron z. Yes. Here by symmetry, it is what's written here.
Yeah.
Here we have, of course, with respect to y, and here we shall have, we are on the second row, so theron to x2, and the third column, theron x3.
dy and dz.
Y and z. And that's all. Because the other position here is by symmetry. It is this one. Here it is this one. And here, of course, it's in respect to times with respect to z. Okay. So tomorrow we shall discuss about applications of extrema. First of all, conditioned extrema. And also some, we shall see the method of least squares and some other application, the regression line, whatever. Okay. So check on the Microsoft Teams at your class. I think at your class, at the Rose class, I put at the Calculus 2 class. You have a class on Microsoft Teams. Calculus 1, sorry, and there you have all the materials. Yes, I completed. I put there all the materials, and I think my colleagues from the seminars also they added a lot of other materials. But at least from the lecture you have many materials and solved exercises and so on. Okay.
Thank you.
Okay, for nothing. Meet you tomorrow.
Yes. O seară bună, la revedere!
La revedere!